Hi, my name is Harris Hosh.
My name is Suyang Jang. Today we'll be talking about MOSFET amplifier applications. The first application we'll look at is the high-gain common source MOSFET amplifier with an ideal current source. If we hold the current to be subthreshold, the voltage gain simplifies to be negative kappa over sigma. You can see that there is no dependence on the bias current, only on the parameters of the MOSFET. However, for above threshold currents, we can see that the gain is proportional to the IREF. If we replace the current with a pFET instead, we introduce a new parameter sigma p to the denominator. Thus, the gain is less than the ideal case. To maximize our gain, we increase kappa and we decrease the sigma for our MOSFETs.
This graph here depicts a transfer characteristic for the high gain amplifier. Notice that the gain region occurs here at this drop-off, and it occurs at approximately at 0.62 volts. For the green line, which indicates our simulation model, the slope was not as steep and therefore the gain was not as high. If we zoom in on the linear region, we know that the slope of the line is proportional to the gain, and therefore we can calculate the gain, and then knowing the typical kappa values and early voltage values, we can create a reasonable gain, which is matching the data gain.
Next, we'll look at the differential pair circuit. For this circuit to work as we want to, we must assure that the current is under threshold. So if we assume that I reference is subthreshold, we can assume that I1 and I2 are both under threshold because IREF equals I1 plus I2. Also, we must assure that the drain to source voltage is above 100 millivolts so that the MOSFETs are operating at saturation. Next, let us look at the I1 and I2 formulas to see what happens in the extreme conditions when V2 is greater than V1. In this case, the exponential dominates for I1 and thus becomes 0. However, in this case, the exponential goes away and becomes IREF. And we can see these are going to be our asymptotes for extreme behavior. The vice versa happens when V1 is much greater than V2.
This graph here depicts the currents for the differential pair and the simulation that we performed. I1 is here in red, I2 is in blue, I1 plus I2 is in black along the top, and our simulation values are in green. Here is the graph for the exponential fit for the current 1. We know from the previous equations in class that we could simplify to this formula here, with this exponential formula. And therefore, we can zoom in on the linear region and relate it to kappa over UT, and therefore determine the kappa value for this slope. The same process can be done for I2, simplifying the equation to this exponential formula here, and therefore relating the slope to negative kappa over UT and determining this kappa value. As to be expected, the I reference is held constant at 8.1 nanoamperes. We also know that the differential current behaves like a hyperbolic tangent function, and therefore if we focus in on the input region approximate to 0, we know that the differential current approximates to this linear behavior as seen here, and therefore we can relate the slope to kappa over UT and therefore determine this kappa value.
Finally, let us look at the transconductance amplifier circuit. We've taken our previous differential pair circuit but have added a current mirror on top so that our output is directly I1 minus I2. This graph contains our model, or our simulation model in green, and our data in red, and then a tangent or hyperbolic tangent as a reference point. We can see there's two main asymmetries between our data and the reference. One is the input offset here, and the other is the difference between the asymptotes in the positive and negative region. We can attribute these asymmetries to the current mirror because when V2 dominates and I2 dominates, there is no need for the current mirror. However, thus creating a small asymmetry here. However, when I1 is dominating, that current must be reflected to the other side, thus creating this large asymmetry here. If we zoom in on the origin, we can see in blue the differential pair, and in red the transconductance amplifier. And when these, or where these graphs cross zero current, is the input offset. And you can see that there is an additional input offset for the transconductance because of the introduction of the current mirrors. Finally, we'll observe what happens when we change Vout and the effect of it on the input offset. You can see that the drain of this second MOSFET is connected to Vout. Thus, if we increase VD here, we increase I2. To account for that difference or increase, I1 must also increase by adding an additional input offset to the input here. Thus, the increase in Vout is directly proportional to increase in the input offset.
These graphs here depict the relationship between gain and the small signal parameters. For the Vin versus Vout, we can relate the slope of the linear region to the gain. For the Vin versus Iout, we can relate the slope of the linear region to the transconductance parameter. And for the Vout versus Iout, we can relate the slope to Gout, which is inversely proportional to Rout. With the data, we can determine the values as seen here. However, we can also recalculate the gain knowing that GM times Rout is equal to the gain and have a gain match. The same process was performed for our simulations for both the gain, the GM parameter, the Rout parameter, and then therefore repeating the same calculations above, noting that GM times Rout and having the same match. This concludes our discussion for the transistor amplifier circuits.